Hi, in this video of Inkpot, we are going to be continuing with the different types of matrices, and we are going to discuss some extremely important types of matrices which are going to have a lot of usage in linear equations and system of linear equation solving. So all of that all of the things that we're going to discuss in this video are extremely important in terms of the kind of applications that they have at a later stage. After this, we are going to have a short assignment on the different types of matrices. So the first type of matrix that we consider is an involutory matrix or an involutive matrix. It is called both, even though the proper word is actually involutory. So an involutory matrix is essentially a matrix that is its own inverse. That is, A into A is actually equal to I. And essentially involutive matrices are all square roots of the identity matrix. Recall that this is different from an orthogonal matrix, which is essentially that A into A transpose is equal to I. This is essentially saying that A square is I, which is saying that the matrix is the inverse of itself, whereas here you're saying that the matrix transpose is the inverse of itself. Now, an example of it, or a question on it rather, is that you have to show that a particular matrix, let's say this one, is an involutory matrix. So what you have to do essentially is calculate A square which in this case is just A into A, and you will understand that this actually turns out to be the identity matrix. I can actually make this calculation happen here, so why not do it. So you have 3 into 3 9, minus 0 plus 0, whatever, it doesn't really matter, minus 8. Okay, that's the first element. So again, inverted L. Okay, then you have minus 12 plus 4 plus 8. Okay, then you have 12 plus 0 minus 12, so which is, both of these turn out to be 0 actually. Then you have 0 plus 0 plus 0. Then you have 0 plus 1 plus 0. Then you have 0 plus 0 plus 0. Then you have minus 6 plus 0 plus 6. And you have plus 8 minus 2 minus 6. And you have at the end minus 8 plus 0 minus 9. Sorry, plus 9. So you have 1 0 0 0 1 0 0 0 1, which is the identity matrix right here, or the unit matrix, whatever you'd like to call it, and that is why A is an involutory matrix. Now you can also check that the identity matrix is also trivially an involutory matrix. I would suggest check it for I3, and it's just a fun exercise and something which is an interesting trivia to remember. Now we come to a type of matrix which is called as the triangular matrix, or the triangular matrices, which is the class of matrices which may be upper triangular or lower triangular respectively. Here I'm using my personal notes because different places would give different definitions of triangular matrices, and I would like us to follow this one. This is the standard definition used in several mathematics books, but this is not something that you would probably find in Hammond, mostly because the way that Hammond explains this is not very similar to the way we are going to go about it. But trust me, this is easier, and frankly, I find it better, which is why we're going to be choosing this one. So a matrix is triangular if it is either upper triangular or lower triangular. Now what does upper triangular or lower triangular mean? Essentially for upper triangular, what you define it as is that Aij is equal to 0 for all I is greater than j. Now I'm going to put a standard matrix here so that this becomes a little easier to understand. Okay. This is a standard 3 cross 3 matrix, right? What you're saying is that aij is equal to 0 for all I greater than j. Now, like I had said earlier, you should always remember that I represents the row, j represents the column. So, I greater than j would mean that the row number is actually greater than the column number, which is going to happen for, if you look at it very carefully. So, this is the principal diagonal of the matrix. I'm sorry about this stupid to see. So, as I was saying, this A11, A22, A33 is actually your principal diagonal. Now, here if you look at it, I is greater than j, 2 is greater than 1, 3 is greater than 1, 3 is greater than 2. So, here is what you're referring to when you say that you're referring to an upper triangular matrix. So what you're saying is that all of these elements are going to be 0, and in that case it's going to actually be an upper triangular matrix. And if you think about it, when that happens, all the weight of the matrix, like I had said earlier also, all the weight of the matrix is going to fall on the upper triangular portion, which is this portion right here, because this is the portion which is not equivalent to 0. So, and the diagonal is always when you look at strictly upper triangular matrices, this also becomes 0. So the diagonal is kind of like middle ground. But what you're saying is that anything below the diagonal is going to be 0 for it to be an upper triangular matrix. So, and the way to remember it is that all the weight of the matrix is going to fall on the upper portion of the matrix. Okay. Similarly, for lower triangular, it's the exact opposite. Aij is equal to 0 for all I less than j, which means that all of these elements actually become 0, and all the weight of the matrix is going to fall on this particular portion of the matrix, which is the lower triangular portion. And to just give you examples, very simple ones, T1 here is the upper triangular matrix, whereas T2 is a lower triangular matrix, and you can see that like I had said, the weight of the matrix is falling at the bottom triangle for the lower triangular, and it's falling at the upper triangle for the upper triangular. I am very, very sorry about my horrid art, but you can see that the weight is falling on the upper triangle. Okay. Now, as I had said, for strictly upper triangular and strictly lower triangular, the only thing that changes is that the inequality actually, here the inequality doesn't have an equality sign, but here it does. So instead of just saying I greater than j, you say greater than equal to and I less than equal to. So what essentially happens is that the principal diagonal necessarily has zeros for both strictly upper triangular and strictly lower triangular matrices. Okay. Now, again, just to give you a little bit of trivia, sometimes it is asked as a 1 marker in the exam, where you are asked, okay, what about the null matrix? So the null matrix is actually strictly upper triangular and lower triangular, both strictly. So this is strictly upper and strictly lower, because it's all zeros essentially. The identity matrix, on the other hand, is upper and lower triangular. However, there's no strictly here, because clearly the diagonal is the non-zero part of the matrix. Okay. Now we come to a very important question, which is that you have to use elementary row operations to transform the following matrix into a triangular one. Now, whenever you're given such a question, there are only 2 steps that you need to follow, and it's always a good idea to keep in mind these steps when you're starting to do such a question. The first one is to identify the principal diagonal. Okay. And while this may not seem like too much of an issue in case of square matrices, trust me, when you deal with non-square matrices, this is something that tends to get lost, and kind of get lost in what needs to become 0 vis-a-vis what doesn't. So the first thing that you should always do is identify the principal diagonal, because that is your, like I had said, middle ground. Anything above that or anything below that needs to become 0 for you to call it a triangular matrix. The second step is to identify, what type of triangular you want to target. Triangular matrix to target. Okay. Generally, it's always easier to go to try and make the lower portion of the matrix 0, which essentially means that you're targeting the upper triangular matrix. The only reason that I would say it is easier is because the elementary row operations seem a little easier to carry out. Now, right off the bat, the first few things that you should do here is R2 goes to R2 minus 2R1, so that this becomes 0, and R3 is going to R3 minus 3R1, so that this particular element R3 goes to R3 plus 3R1, I'm sorry, so that this element becomes 0. And I have actually solved this out for you and put a cleaner version of it, just so that you don't have to suffer through my handwriting. Okay, so you have R2 minus 2R1, this is what it would render. You have R3 plus 3R1, this is what it would give you. And then eventually, because you now have these two as zeros, you would like to get this as a 0, so you get R3 plus 3R2, and this is what you get. And these three elements actually become a 0, which means that all of the weight of the matrix is on the upper triangular side. So this becomes an upper triangular matrix, because Aij is equal to 0 for all I greater than j. So this concludes this video. Now we are going to have an assignment video for the different types of matrices. This would have several different kinds of proofs. While we have covered a significant number of questions on types of matrices within the videos, these are the kind of questions which would which are of the proving kind, which I would suggest you should look at once and definitely revise later. Thank you.